And like, I can, like as of now, I have like sort of like a setup function which sets up and it gets all the data from like January 1st till present. And then I have one that like updates. So basically, it like pulls all the data where like the timestamp is greater than the last timestamp.
Okay, so where are we? With the homework.
Yeah.
Fifth, sixth, sixth.
Oh, come on.
Sixth.
We just got it.
Maybe next year.
All right, that's not that bad, right? I just a warning. 7 is a bump. Okay, so we'll be more lenient. I know 7 is a bump. We've learned that during many years of teaching this course, and we'll be more lenient on 7. You know, like an attempt will matter a lot. That's where you get support virtual machines. But 6 should be quite straightforward, you know, and then we may have to shrink very severely homework 8 down to 1 exercise that we absolutely need to do. That's K&N classification. You guys have to know what that is. It's a very simple thing. If we get out, and we may end up putting that exercise in homework 7, and then we call it 7 homeworks, you know, reduction by 1. Okay, so we need to do stuff so you guys can do homework 6, right? So PCA first, and then image features. That's what we have to do. So again, I have this X matrix, right? This is the data matrix. This is 1, 2, and this is F1 with FE features. And we did something last time we started PCA. We were saying we have this idea of project data on one line. The line is E. E is this sort of tensor vector with the norm equal 1. That is, it just gives the direction of the line, nothing else. And let's make this assumption to save time that the mu will belong to that line. So that mu is, of course, the average 1 over n sum of the xi, the average. We made this argument before. If we're to represent everything by 1 point, that would be the center of the data, the average. So now let's assume that line passes through there. So what we did have is to say, how that line going to look like? Well, there is mu on it right here. And then every point, here's x1, gets projected to, we said, a1. Here's x2, gets projected to a2. And here's x3, here, gets projected to a3. And here's x4, gets projected to a4. Now, because it's on a line, the projections, I don't need to count, those are vectors. Those are d-dimensional vectors, but the projections, because in a line, instead of counting a4 as a vector, I'm only characterizing a4 as a scalar. I'm going to say, I get this point by writing it as mu, this center. There is this E here, right? This is E. This is the, E is simply a directional vector. It's a size 1, just gives the direction of the line. So this A4, I'm not going to write it as a vector, but rather as the scalar that is in the direction of E, how far do I have to go on this line? That's very well specified because the center is fixed, the mu. The direction of the line is fixed, E. So then if I say you got to go 3.75 units on line E in that direction, it's clear where I have to end up. And if I say minus 3.75 units on line E, I go in the other direction. So the first, that's where we get the dimensionality reduction, right? Because we project everything in a line, we have 1D, and then how do we write that down as 1D? Well, we're not going to write A as d-dimensional vectors, although they are d-dimensional vectors, right? This point here, it's still a d-dimensional vector in the original space. We're going to write it as mu plus E times that. So our plan is to have every xk replaced by mu plus AKE. That's what we want. Where mu is this. And then we said there are two possible objectives. So which E, that's the direction. Which line do I need to pick? That's where we left last time. I can say either minimize J, that's the regression objective, which was sum over all the data points mu plus AK E, that is the projection, right? Mu plus AKE is this point, minus the point itself. So I'm minimizing how far away the projections are for the points as a sum over all the data points. Or I could say maximize variance of projections. That is E of mu plus AKE minus E of mu plus AKE. That formula for variance. That's where we were last time. And my last question, I think, before I shut down the camera last time was, are those the same exact thing or not? There was some speculation that they might be the same thing. Did anybody figure this out? Are they the same thing or not, mathematically speaking? The line, the E that corresponds to minimize the square loss is the same E that corresponds to maximize the variance. So that's where we are. Independent of whether you figure it out or not, let's see how that goes. I'm gonna go back to a matrix we've seen before, and that is the empirical covariance matrix or scatter matrix. So the covariance of X, we're going to call sigma, and we're going to use these little thingies here to distinguish between summations and sigmas. Like sigma, the covariance has the little edges, and summations don't have these edges. So this sigma is the same matrix we've seen before, is the sum over all data points of xk minus mu times xk minus mu transpose. This is the matrix of covariance. We've seen this when we looked at this multidimensional Gaussians, right? And the way you can think of this matrix is we'll figure out the dimensionality, right? It's d by d dimensionality. On the diagonal is the variance for each dimension. So this guy here will be, what's the variance for the first column of the data? The first column is x1, 1, x2, 1, x3, 1, up to xn, 1. If I take a look at this column and say, what's the variance of that column? That will be the sum over all the data points for who? xk1 minus mu 1, because I'm only looking at the first column of the data. These are not anymore vectors, they are actually the first column values for either the center or the points, right? Times xk1 minus mu 1, right? That's how empirical variance works. This is really the expected value of some values minus the center square, right? You can see right there in the formula. So by that logic, who's going to be on this corner here? The variance of the last column. So that is the sum over k over xk d minus mu d, xk d minus mu d. Right? So this column here, the diagonal of this matrix, is the variances for first column, second column, up to d column. But who's in here? So now this is column, like row 2, column 1. What's in here? Covariance between column 1 and column 2. So what's the formula for that? If I want to estimate that empirically, what do I do? This will be a sum over all the data points of what?
X2 K1 is mu2.
What? xk.
2 minus mu2 times xk1 minus mu1.
Right. So I don't think we did this when we talked about the covariances the first time, but this will be the right moment, as in not right now in class, at home, but today, to wait, to pause for a second and say, if I understood this in high school or whenever I found out the variance for the first time, which was the distance between the point and the center squared, and summed up over all the values, right? That's how people measure variance. They measure the mean and they get the distances from every point to the mean, square them and sum them up. And average, divide by n, if I want to n minus 1 to be statistically correct, right? That makes sense, but what is this? How, can anybody give me an English version of what this is? I know minus second component, first component, sum them up over all data points, but in English, what does it do? Why is this the correlation between the second and the first? Why is this sum doing that? So I want to give everyone a chance here. Right? So I'm not care too much about the formula. I myself, sometimes I have to look it up, right? I don't remember the formula all the time. But I remember what's supposed to do that formula. For example, let's start with the obvious thing. When I expect a 0 here, independent, right? When I expect this value to be high, when they are correlated positively, which means what? When two columns, column 1 and column 2, are correlated positively, what does it mean in English? High values on 1 correspond to high values on 2, small values on 1 correspond to small values on 2. And if this value, the covariance value, is negative, they're anti-correlated, which means what? High values on 1 correspond to small values on 2. Is this sum doing that? Is it going to give me high values when high values correspond to high values? But by correspond, I mean when I go over the data points, right? Because there's the second column, x21, x22, up to xn2, right? So by high values and low values, I say when I go over all million data points, some of these will have high column 1 values and low column 1 values, and some will have high column 2 values and low column 2 values. Right? Correlation means when you go over the data points, high values on 1 correspond to high values on 2 across the data. So why is this formula gives me that? Without a proof, just intuition, yes.
If x2 is much higher than mu2 and x1 is much higher than mu1, it'll give you a large positive number. But if one is higher and the other one is lower, it'll give you a large negative number.
So now, on average, if high values correspond to high values, I get positive terms. And if low values correspond to low values, I again get positive terms because this is negative, that's negative. And when high values correspond to low values, one is positive below, over the mean, its own mean. The other one is negative, it's below its mean, right? And then either way I get negative values summing up, I ended up with a negative value. A more mathematical question that I'm not gonna do, but the mathematicians can think about that. How about 0? Like I get it that if it's independent, I shouldn't get too high on the positive side or too high on the negative side. But why independence really means 0, like crystal 0. So I'm asking a more technical question. What is 0? How do you get 0 here representing the independence? In other words, I get it that positive value corresponds to positive correlation and negative values correspond to negative correlation. But maybe the center of this independence-dependence thing, it's not at 0, it's at, I don't know, 2.5. Why is it at 0? So that's some exercise that we do. Okay, so I think we're going to call this a scatter matrix or a covariance matrix. This is empirical covariance. It's like what people estimate from data. And a very important thing we need here is that if we call these values, pi, I, 1 pi, d, and pi ij, the rest of it, right? Like as in the values, variances for variances. Pi ij obviously is going to be the same as pi ji, right? Because if you look at this product, what will be here at 1, 2, you get the same exact value, right? That's easy. So how do we call that? That's symmetric. Like this sigma, it's equal with its transpose. That is, if you reverse it by the diagonal, you get the same matrix. And another property that we need, and I'm not sure how many people have heard of this, but we don't need it like with proofs. It's semi-positive definite. That is, as a definition, if I take any vector z, any vector z, if I do z times sigma times z transpose, I have to align the dimensions, of course, to work out, because these with d by d, so the vector must be 1d times sigma times d1. This is always a positive one. So for any vector of real values, this is a very, very important concept in linear algebra, semi-positive definite matrices. And they expand to matrix differentials. Every time you have such a matrix, it's an amazing property to have for all kinds of linear algebra operations. And the symmetry, it's also an amazing property to have for linear algebra operations. That's why these matrices, the scatter matrices, aka covariances, have all the nice properties that linear algebra wants. So working with covariances can be extremely fast, even if they're big, because of those two properties. So in particular, MATLAB is the king of linear algebra. It can do very, very fast operations with matrices. In particular, this matrix, we're going to get to it in a moment, admits a spectral decomposition in Eigen Values, which is extremely useful for what we're going to do now. Okay, so not all of that is necessary for PCA. You don't need to know all of that. You need to know this, which is obvious, symmetry. And you need to know not the formula. It's okay to look up the formula 6 months from now or 6 years from now, but you need to know what is covariance supposed to be in plain English. So I'm going to go back to this. And let's look at who this is, this guy here. So I'm taking on this objective 1, objective 2, and I'm taking objective 2 here. And I'm going to say, this is E of AKE square. Kind of got rid of that mu in there. That's a simple thing because the average of this is going to be mu, right? That's what it is, right? And then mu goes away with this. And in here I'm going to get expected of E transpose So these are very simple steps. I got rid of the mu, then I replaced AK from this equation here. I say AK is XK minus, let's see, so how that works. XK minus mu. Right. So I need a little bit of manipulations here with this E of AK. So what did I do here, right? This product is the square AK has to correspond to this quantity right here. Why is that? I'm missing an E somewhere, but that one that goes away. Am I missing an E or am I not? So ET, it's here. This summation here, the expected value will give me this because ET, E, you see this is the sigma inside. So now I have the question of why AK here corresponds to XK minus mu. So how do I get that to work? For this to work, there is a property that we need, which is E times E transpose must be 1. Right, because otherwise you can see how AK is missing, it has an E here, right? AKE is that, but then I'd have more E's than I have here. The reason they got away is because of this property, and this is coming from where? Who is this? This is the normal field, right? And this is that because E was from the very beginning just a unit vector. It was just the direction. I mean, the value 1 doesn't matter here. It's just a fixed value. I don't want E to influence. All the E's must be tensor vectors, right? I don't know if this is clear or not. This is a property that comes from this unit here, right? And then I need that property when I open this AK with E's in it to get rid of some E's in there. Hands up who's with me. At least in principle, where we want to go with this?
What E's are you getting rid of? Don't you have just AKE times AKE?
Yeah, but who's XK minus mu? That's AKE, right?
Gotcha.
So I have some extra E's in there that need to be get out.
Should it be ET? There should not be 2 ETs. There should be 1 ET and 1 E. That way.
That we have to see the dimensionality, right? So for this thing to work, dimensionality has to agree. You're saying this is just E?
Yes. So that way, AK got substituted by XK minus mu, and E into ET is 1 because they are orthogonal.
So is this to correct or incorrect? What dimensionality do I need here? Maybe here it's. I think the dimensionality of this, if it's put it this way, it has to be the same as this, otherwise they don't multiply correctly, right?
So we did XK minus
In
mu.
there,
over
it
there.
moves
Yeah,
the E.
it works like that.
So I think this is correct. Because if I put it on this side, then it multiplies to the right, but if I put it on this side, it multiplies to the left. If this multiplication works, for this to work, it has to be in the same direction. I mean, I don't insist on, you can consider X column vectors or row vectors, whatever you want, and then E's got to be column vectors or row vectors, but the multiplications dimensions have to align, otherwise it doesn't work. But every time you do this kind of thing, or at least when I did it the first time, I always have the trouble of, before we go to the dimensions, what is this whole thing? What am I supposed to end up with here? Is this a value or a matrix? This inside the E, what is it?
So scalar.
Am I trying to obtain here inside the E? Or what? A value, right? So when you align the dimensions, this whole thing has to end up being 1 by 1 dimensional. Okay. This may be something that if it's not critical for the class, but if you need to understand this, you may have to put it down on paper. The easiest way to do those things is to take a 2 by 2 or 3 by 3 examples and literally compute all these matrices. Okay, how about this guy? So everybody can see this is exactly the scatter matrix, the covariance that I've got in here, right? Good. How about this? Who is this? So now this objective, if I try to work that out, J is sum over all k of AK squares, k equal 1 to n, minus 2 sum of AK squares, plus sum over k of xk minus mu. Square? Let me write it down and then we'll see how far we can get with the derivation. So let's see what happens. If I decompose this with the formula, what is it? Mu minus xk, that's a thing. And then ake is the other factor. So I have here is it an a minus b squared? That's a squared plus b squared minus 2ab, right? So every square how do I get from here to here? I think I applied the formula a minus b squared is a squared plus b squared minus 2ab. You guys know this formula, right? So who's who in here? xk minus mu is xk minus mu, that's say one of the terms, and that's the sum of squares. The sum remains the sum from the beginning, right? And then the other square, b squared, is where? First term. What happened to the e? E times e got 1, right? And now, where is the minus 2ab? This is in here.
Here, xk minus mu got
Right, so this will be, in here it comes from 2, it's a sum of course in front of it, 2 ake, that's the first part, and then mu minus xk, that's the second part, right? The mu minus sk is ake, so I get the ak square again. Okay, so now moving down, this part remains, whatever I have the sum of squares stays in here. This is important for me to leave it as it is because it has no e in it. Like, let's think about conceptually for a second. xk are the original points, right? And mu is their center. This difference does not depend on e. Right? I can pick any line, the difference between the points and their center will be the same. So that I'm going to leave on the side because as far as deciding e, this doesn't matter. Any e will have the same exact difference. And then, sum of a squared minus 2 sum of a squared, I only need one of the a squares, so I have only minus 1 sum of the a squares. But who's a? A is et times this difference, so that's a in here. And I write it this way to get the same matrix I've had before. Because now if this is ak, I replace it with this. When I do the product, I get exactly the same derivation like before. Hands up again, who's with me? Okay, at least the idea of what's going on. The thing with those matrices, if we really want to go down into details, we have to put it on paper. But I open up those squares, I manipulate, I always take care of E times E transpose, that has to be 1 because the norm of E. And the other thing that it's implicit in what I want to do here is I want to get rid of the part that's without E. This is the same as in, remember at some point early on we did a decomposition of square error into natural error of the classifier plus bias square plus variance. That's kind of the same thing. It's kind of how much noise you have, there's nothing you can do about it. The rest depends on the line you pick. But there's a notion of noise that's the same for any line. That would be this term. So because I've got to here, I'm going to say this term here, it's this term here, with minus, because I have a minus in front of it, Et sigma E, that's this term, the same as this. But this one has an additional thing, plus sum over all k, xk minus mu squared. So now I'm back to the question. Minimizing this or maximizing that, would it give me the same E? So I'm looking at those two. On one hand, I want to maximize this quantity right here. Maximize as a function of who? E. I'm looking for the best line to do the projections on. So I'm looking for E. I want to maximize this. Or I want to minimize this whole thing. But this is a constant as a function of E. I mean, it depends on data, of course, but the data is fixed, it doesn't matter. So in terms of minimizations or maximization, this is the same. Now you can clearly see maximizing this or minimizing that is the same exact mathematical objective, which justifies the whole thing. Okay, so we're good so far. I think that clarifies a few things because the question is very pertinent, not mathematically, but those two make good points of what do I want E to do or to happen, and it turns out they're the same thing, which cements our notion that this is certainly the best projection you can have on a line since it achieves both objectives. It's not a coincidence this happens. This is all due to the square laws, which has this property, which you've seen before. So how do we do it? Either one of those things. How do we now make it work? Like, how do we find E? Like, I mean, the fact that it corresponds to the same exact thing doesn't mean that we know how to find E yet. So I'm going to rewrite this problem. I'm going to say our problem is to maximize Et sigma E subject to constraints. What is my constraint? Like that's what I want, right? We just said this. You want to maximize this or minimize that means the same thing. But there is a condition here. Yes. Because that's what we said, E got to be this tensor vector. You can easily see that if you multiply E with a constant, you can increase that arbitrarily. Now, there is a technique that we avoided for a long time to put our hands on it. It's the equivalent of gradient descent with constraints. Without gradient descent, what do you do? Without constraint, what do? You take the objective, you do what? Take differentials, set the differential equals 0, and that's the maximum or the minimum. It will be clear whether it's maximum or minimum because it's either this function or that function, right? That's what we've been doing for so long. Taking the derivative, set it to 0, that's the point you want to go. I'm not available. So, what if I have a constraint? How do I do that? I want to take the derivative, set it to 0, but I want to be aware of this constraint. There is a technique that goes hand in hand with gradient descent, which is called Lagrangian Multipliers. And to put the icing on the cake, we're going to postpone this one more time, okay? We're not going to do it today, but we'll do it, okay? Promise. By the end of the term, We're going to figure out how Lagrangian multipliers work because it's essential. You need to know that. Even if you're not a mathematician, even if you don't end up doing numerical optimization, you need to know three things. Gradient descent, four things. Gradient descent, coordinate descent, which we're going to do. Newton's method, which was optional, I think, at some point. Most people could have even implemented that, right?
Yeah.
And we need to know Lagrangian multipliers. So we'll make sure before we get out of here in April, a month from now, we know those four things. Numerical optimization is much more than those four things, but you need to know those. So we need a Lagrangian that is saying, the theory of Lagrangian multipliers says what you want is to set a new objective, which is the old objective, minus some sort of constant around my constraint. So my constraint, I can write this constraint here, E transpose times E minus 1 equals 0, right? That means the same thing. Because E transpose times E is the norm, so minus 1 would be 0. And Lagrangian multipliers, the theory, which we don't do, but we'll do it next week. The theory says what you want to do is to have the same objective plus a Lagrangian multiplier, that's this alpha, per constraint. In this case, we only have one constraint, so it's only one Lagrangian multiplier. The constraint is this. Because this equals 0 means exactly the constraint. So we'll figure out why later, why this exactly gives the solution we want, but for now you can just trust me, I hope. Okay, so then it's back to gradient descent. We have this objective we want to do. What do? We take the derivative, right? So what's the derivative at E? Because E is the one we care about here. E is our variable. How do we differentiate this with respect to E? This would be 2 sigma E, right? Minus, if I differentiate that in there, is 2 alpha E. Because this is like E squared, right? I'm trying to cheat here, like skip some mathematical vectorial mechanisms. So I say this is E squared, and I differentiate alpha times E squared. What's the differential in unidimensional space? 2 alpha E, right? That's like it there. If you're really a mathematician, you have to verify that this works with vectors. And this, the differential has to be 0, right? Because it's 0, I get sigma E must be alpha E. Now, what's going on here? Sigma is the covariance matrix. So what's the dimension? This is d by d, right? E must be, again, to be the alignment. I maybe messed up the transposes in here, but this gotta be d by 1, otherwise it doesn't work. Alpha is a scalar, that is 1 by 1. And this is d by 1. Does it work? D by d times d by 1 equal 1 by 1 times d by 1? Right, it works. Now, this is an important, hugely important linear algebraic property. And the way to see this, if you don't want to go to the linear algebra, is to say, E is a vector, example, which we don't know. We try to find out E. That's the whole point is here, to get to E, right? E is a vector. When you multiply a matrix with a vector with a matrix, often, almost all the time, you change the direction of the vector. It's not just the size, you know. E times a matrix, A, it's a different vector, right? And when you multiply a vector with a scalar, what happens?
You change the length.
I don't change the direction, only change the size, right? Because whatever E is, if the alpha is 2, then it's going to be, you know, alpha E. So in general, when you multiply with a scalar, you never change the direction, just the size. And when you multiply with a matrix, very, very often we change the direction. There is only a very particular case of vectors and matrices that have the property that when you multiply a vector with that matrix, it does not change the direction. That's what's happening here, right? E multiplied with the matrix has the same direction as E, which is the same direction as E. Directionally speaking, E didn't change the direction here, and because those are equal, it doesn't change the direction when I multiply with the matrix. In terms of rotations in geometry, this matrix has no rotation power over E. It doesn't change the direction. It only changes the scale. This particular case only happens when E must be what vectors do not yet change direction by multiplying with matrices. There's only very few cases when this happens. E must be an eigenvector of sigma. And alpha must be the corresponding eigenvalue. It's corresponding eigenvalue. It's not a random eigenvalue. Every eigenvector can pair it up to an eigenvalue. This is actually the definition of eigenvectors. So even if you've never heard of that before, you should have, but if you didn't, specifically the vectors that don't change direction, aka multiply with a matrix is the same as multiply with a scalar, are exactly the eigenvector of matrix sigma, and the corresponding scalars must be the eigenvalues. So that's the definition. There's no new theorem that we need to do. This is a critical property of linear algebra. If you take a basic course in algebra, by second month, 4 or 5 weeks into, you're going to get to eigenvalues. Okay, so now that we have that, we know it's an eigenvector. How do we get which eigenvector is it? Like, we know the property from the derivative, it's an eigenvector, so which one is it? Getting eigenvectors is easy, because we can decompose the matrix and get the eigenvectors and the eigenvalues. But every eigenvector will satisfy this property. Every eigenvector will have some alpha that works out. So which eigenvector we want to maximize this quantity? So because we have a maximization problem, that means we want the eigenvector with biggest eigenvalue. There is a more theory here that I'm going to skip that says, given what you have, if you were to add a second dimension to the data, so all this theory was based on, I want to project my data on one line. Now that I've got that first line, somebody may say, okay, if you were to have 2 lines instead of 1, which one should be the second line? So assuming we have these projections, what is the next line to use, so to speak? So I can redo the whole derivation and then say, on a second, if I want to use 2 lines, 2-dimension projections, that will be use E1 and E2, right? I now have 2 lines. That will be, okay, here's another line that passes to the center. That's E1, and this is E2. Which one E2 should be? Without doing the derivations, what do you think is going to happen if I do those derivations? Another Lagrangian, another derivative. Who is E2 going to be?
The next biggest one.
The next biggest eigenvalue vector. Like, I got the second eigenvector corresponding to the second biggest eigenvalue. So if I want 2, then E1 stays what it is, and E2 is the eigenvector corresponding to second biggest eigenvalue. And I can keep going. If I want 3 dimensions, I'll take 3 eigenvectors in the order of their eigenvalues. Yes?
And this corresponds to reducing the space from like d-dimensional to 1, 2, 3.
Right, that's what we're going to do next. But it also corresponds to something else. So I want to walk a fine line between what we actually achieve in data, is what you're saying. So he said it in a very nice way. What he meant is the following: hey, you know what? That's all very good, but what is this buying me? That's what's the point of all this? The point is I'm going to reduce the dimensions to 1 or 2 or 3 or 20 dimensions. Right? We'll see that in a second. Geometrically, if this is the case, you can think about this in a different way, but that doesn't facilitate the math. But thinking, it does. You can take the d-dimensional data, x, and first rotate it. There's no change, just rotate the whole data. It's equivalent to take a figure and rotate the axis in such a way that axes now align with E1, E2, E3, the eigenvectors. That is possible because of some condition in there. That is, eigenvectors are orthonormal. They're perpendicular to each other. And original axes are also perpendicular to each other, right? In a Euclidean space, the dimensions are perpendicular axes to each other, right? So because those are perpendicular and the eigenvectors are perpendicular to each other, I can take the original matrix and kind of fit it into the eigenvalue axis. So now that I fit it in, the whole reduction is much simpler to understand. It's just saying take only 3 coordinates out of your data. If I tell you already the axis of the data, which are d axes, align with the d eigenvectors, the whole reduction says just take the 3 highest variance axes of the data. So if you have 50,000 coordinates, just take the top 20 or top 3 or top 2. But the first step is to put the data in the axes that correspond to the eigenvectors, which implies a rotation, which implies that the new features that we're going to get with PCA are not simple feature selections. That would be the case if the data was already in the eigenvalue space, because we're just selecting the top 3 eigenvalues. But since we have to rotate it, every new feature will be a linear combination of the all features, because that's what rotation matrices do. They put a linear coefficient on your, a rotation corresponds to multiplying with a matrix, right? And then every new column in my matrix, it's a linear combination of the all columns. So in PCA, we don't get some column and some other column and some other column like feature selection. We get that after a multiplication with a rotational matrix, which means every new column would be a linear combination of the original ones. So we have these 2 points of view of what PCA does. So let's look a little bit at how does this work.
You said we get E1 and then we get E2, and then we get a 2-dimensional space. So does that mean we take the plane that's spanned by those 2 vectors?
Yes. So there is a question implicit there, is this iterative procedure optimal? If I get E1, then given E1 stays, I get E2, then I get E3. It's the same as globally optimal getting 3 at one shot. Because sometimes in algorithms you have this problem, if you go greedy 1 by 1, it's not as good as if you just get optimal at the top 3. In this case it is. Getting it in order of eigenvalues is the optimal ways to get the dimensions as far as PCA is concerned. So I want to show you a little bit of linear algebra here. But again, it's the intuition that we are trying to get, not the formulas. So here's how this looks and why it's so easy to do for the covariance matrices, because of those 2 properties. So because sigma, the covariance matrix, is symmetric and it's semi-positive definite, it means the eigenvalues, the AI, are orthonormal. That is EI, every eigenvector times itself is 1, and every eigenvector times another eigenvector is 0. They form a nice axis. Everything has unit 1, 1, 1, 1, 1, right? And then every other one is perpendicular to the rest, so they form a perfect Euclidean system of axes. That way. Of course, may not be the same axis the data has, so we have to rotate the data to put it in that system of axes. Okay? And now, the spectral decomposition, there's other goodies here. Eigen values are all real numbers, etc., that works out. It says, let's look at the matrix C, that's the eigenvector columns. So E1 is a column. I'm going to write this E1 with a line that says, that's the first eigenvector, second eigenvector, up to the D eigenvector, this matrix C. And then, because they're orthonormal, what happens if I multiply C with this transpose? So I'm trying to show you the spectral decomposition, which I can only do for the nicest possible case, which is this sigma that has those two properties. The many decompositions of matrices is very useful for different purposes, like singular value decompositions, most people have heard of. This one you should know for the covariance. Covariance, it can be applied to any matrix that's of the form X times X transpose. Is covariance of this kind of form? What's the difference between the covariance matrix and just doing X times X transpose?
Actually, transpose works if your data is already centered.
It's the same thing if the data is already centered, because what this is X times X transpose, except it subtracts the center out of it, right? So anything that looks like X times X transpose doesn't have to be, I mean, it looks like a covariance matrix apart from the centering, has these two amazing properties. Symmetric, because you can easily see if you apply the transpose, you get the same thing here. And you can easily see this other property too. Think about it, Z times X transpose times Z transpose, that's whatever the name is, semi-positive definite. This is actually a sum of squares. It's Zx times Zx transpose, which is a sum of squares, so that's always going to be positive. So these matrices are the nicest linear algebra matrices that you can ever hope for. All the way back to the regression, first class. You remember that matrix in the normal equation? There was an X times X transpose inverted in there. That's why we have a closed form for regression, because we get to this nice matrix, otherwise there'll be no hope. All right. So if I multiply this C times C transpose, what do I get? I get the identity matrix, which is 1, 1, 1, 1, 0, 0. Why is that? It's easy to see. On the diagonal, it's always an EI times EI transpose. That will give me 1. And outside diagonal, it's always an EI times EJ, which is always 0. Hands up, who's with me? So are we getting these two properties? All the norms are 1. And when you multiply two of those things, you get 0. So the way to think about this is these are axes, perpendicular axes. This is in 3D, right? So when this is 0, 1, 0, 1, 0, 0, 0, 0, 1. All of them have norm 1. And when you multiply dot product between any two of them, you get a 0. Those properties means when I multiply this matrix with this transpose, who's the transpose? E1 is here, E2 is now here, E3 is now here. Right? When I take E3 times E3, I get a 1. But when I get any E3 times E5, I always get a 0. Hands up again. Good. So that's the identity matrix. We're going to call this ID because it's in the dimensions. So now I'm going to say the matrix sigma, I can think of it as sigma times ID because multiplying with identity matrix doesn't do anything. That's how you obtain a spectral decomposition. This is sigma times E1, E2. I'm going to write this in free form, so you guys can see. These are the column. This is the C. So C times C transpose, that's ID. Right, that's for everybody to see exactly what's going on here. This is the C, and this is the C transpose. And now what I can do, I can put sigma into, that's something easy to see. Sigma E1 multiplied with so I can multiply sigma with this matrix, and what I get is sigma multiplied every single column. That's just matrix multiplication, right? And then I still have this in here. Now, sometimes it's useful, I'm going to do parentheses after, to put some sigma in here and some sigma in there, but for now, just to follow matrix multiplication, sigma multiply with this is sigma multiply with every column. What I'm going to do is use my eigenvector property, sigma times an E, since E is the eigenvector of sigma, is what? It's alpha times n. Every sigma times E can be replaced by alpha times E, the corresponding alpha, because every E has its own alpha, right? So everywhere I have sigma times E, I can replace it with alpha times E. So this would be alpha 1 E1, that's still a column vector, alpha 2 E2 column vector, alpha 3 E3 D column vector. Times E1, E2, ED, that's the transpose matrix. And now what happens here, if I open up parentheses, I say I get alpha 1 E1 So I want to be very careful of the first dimensions. I mean, you might be tempted to say that's a 1, right?
That's an outer product.
Right? It's a 1, 1, 1. That's just alpha 1 plus alpha 2 plus alpha d. That can't possibly be true, because that's a sum of real numbers. It will be a real number. But I'm clearly stuck with the matrix, right? So that's not it, right? So what is, maybe I got to transpose in the wrong direction, I don't know. E1 for me is of what kind? D times 1, right? It's D rows 1. E1 is, the way I draw it here, E1 is a column vector. So E1 times E1 transpose, what dimensionality is this? D times D. It's another D times D and another D times D. So it's a bunch of D times D matrices, right? And they all have these alphas, each one of them. Because that's why I get D times D matrix as the result. So I think this can be written as, this is just matrix manipulation. I can write it as this matrix I had E1, E2, ED, times a diagonal matrix that's just the alphas, times that matrix transpose. If you open up the parentheses here, you get exactly the sum. So that is the spectral decomposition. That says sigma is the eigenvector matrix times the diagonal of eigenvalues, alpha 1 up to alpha d. The rest is 0. This is a diagonal matrix in here. This is 0, 0. Times the eigenvalue transpose, spectral decomposition of these very nice symmetric semi-positive matrices. So now we can see what he asked just 5 minutes earlier, which is what happens in PCA from an algebraic standpoint. How is this going to work? If I look at this decomposition here, maybe this is the most useful. Eigenvector, again, that's D dimensions, right? D alphas, and then the other way. What am I essentially doing in PCA? If I pick just one, I'm going to have only E1 times alpha 1 times E1 and nothing else. So that means I'm replacing the covariance matrix just with the first term here in this summation. And I'm ignoring, I'm saying the other ones are 0. If I want 2, I'm getting E1 and E2 times alpha 1, alpha 2, the rest are 0 times E1 and E2 transpose. So now I get 2. Of course, that also controls the rank of a matrix, right? If I destroy a bunch of alphas, I make them 0. And if this is then think about this C, that C, which is D by D, right? Then this is the alphas, alpha 1 to alpha D diagonal, 0, 0. And then I do C transpose. That's also D by D. This might be full rank, meaning D rank. If I replace all except 2 with 0 alphas, so I just keep alpha 1 and alpha 2 in place, and I make the other one 0 for the diagonal, the rank of this matrix here will be, then automatically the rank of the whole thing will be 2. So in terms of the rank power of this matrix, if I only keep 3 eigenvalues, I'm going to get a matrix of rank 3. That means everything in that matrix could be my representation certainly can be written as 3 independent coordinates. I don't need more than 3 because the rank of the matrix is 3. Okay. So now, I have another proof here about orthonormality. Like one question that at some point I was doing is to say, why do I get this? So that's an exercise. This is a constraint. Since it's just directional, we can set the size of this is, then we don't need to have different sizes. But this here is an exercise. Why is it that the eigen vectors, if you multiply 2 of them, you get 0? That's essential to allow the rotation, right? In order to take my data, which has perpendicular axis, and rotate it into a set of new axes, those new axes have to be perpendicular to each other, otherwise it won't work, right? So why is this, coming up for these two properties? So now, in practice, if you use PCA in MATLAB, which is what I'm going to show you in a second, how is this going to work? Let me erase something. So now if we look at the rotational aspect of things, PCA, geometry. Algebraically, we saw what's going on here. I have a spectral decomposition, and I replace a bunch of eigenvalues with 0. I keep 1 or 2 or 3, how many dimensions I want, and that determines the number of dimensions. But in practical terms, you can take my data matrix X and first rotate to C, which is, again, E1, E2, ED axis system. If those are perpendicular axes, there's always a rotation matrix that does the rotation. From any system of perpendicular axes to any other system of perpendicular axes, there's guaranteed to be a rotation that does that. Right? So that is essentially rotate to this system of axes. That means X has to be multiplied with some. This is the rotational matrix. Rotation matrix. So X is n by d, and if I rotate it, what this P should be? A rotational matrix is? D by d. So the data is still n by d. It just got rotated from its original space into some other axis now. It's still dimensional data. But now that I have it in my system of E eigenvector systems, what does dimensional reduction mean? Just select the first few coordinates, right? So this is step 1, rotate the data. Step 2, choose k coordinates. So that means my new matrix X times P, which is this matrix now. I still want to keep all the data points, but I'm only going to keep k columns and ignore the other ones. So I'm chopping the matrix. I'm saying keeping the first 20 columns. Again, I'm working with this matrix that's being rotated now, and ignore the other columns. That's already sorted by the eigenvalues. So that's corresponding to making some eigenvalue zeros. And if those are already close to zero, I don't lose much information in there. You'll see that in data, especially in easy data, it's typically the case that the eigenvalues that are significantly away from zero cannot be that many. Like, you don't need to get crystal zero eigenvalues, but on the data that I'm going to show you, which is 70,000 images on 780 features D, there are only like 5 or 6 or 7 features that have an eigenvalue significantly higher than zero. The rest are pretty close to zero, which means by replacing it, calling a PCA, and only keeping enough eigenvalues like 10, we're not losing much of the data information, even though I started with 780 dimensions to start with. So let's play with that a little bit, and then I'm going to talk about something else, if we have time. MATLAB, my favorite, especially for linear algebra. If you want to be a data scientist, you gotta know Python. I mean, if you want to be a computer, if you want to be anything, you gotta know Python. There's no way to avoid Python, okay? It's too bad. Like, unless you want to be an artist of some kind, but even then you might need Python anyway. So you gotta know Python. In data, it's useful to know MATLAB, especially if you do stuff that requires some mathematical manipulations. And as a engineer, machine learning engineer production, you need to know Java, because most of the production systems are written in Java or C, but C is really down level programming. Java is what's used in most of medium-sized companies. So this is MATLAB, very good with linear algebra, by the way. What do I have here? In my memory, I've loaded this matrix of digits, right? And then I cut out of it the X, which is the, you can tell, 70,000 images, 784 pixels each, right? So that's like 8 by 28, 784 dimensions. I think those are like black and white pixels. That's the same data you have. And then the 70,000 of them. I got the L, that's the labels. The L is really just labeling which digit is it, 0, 1, 2, 3, up to 9, right? And I also run these k-means here. I have a special k-means, not the one that comes with MATLAB. I got downloaded the package. That we're familiar all with k-means, not exactly what it, like how it works internally, but what's the purpose? It groups those 70,000 images into clusters, and Y will be the assignment. This is Y20, let's go to Y. So this will say, give me a cluster ID. This is not the Gaussian k-means, it's the hard k-means. That says, give me a cluster ID for every one of the 70,000 points. And I tell him I want 10, so everyone's gonna get a label from 1 to 10. Now those labels, 1 to 10, don't correspond necessarily to the annotation that picture corresponds to digit 5. It's just clustering IDs, right? So I can run this and I get k-means. So the size of Y should also be 70,000 things, right? Because everybody gets one value. Okay. So now, if I call in MATLAB PCA, remember, PCA doesn't use the labels, right? So we didn't go there yet. It just look as the X matrix. So the whole rotational, choose the top eigenvalues, all of that have nothing to do with the labels. PCA is useful in the context of clustering that way because in clustering we don't have labels. This P here are those rotational coefficients. Where do we put that? I guess it's behind this board here. So what we said is geometrically we have two steps. I'm going to put the first step in here. First is to move X to X times P with rotate. So that will put this matrix on the eigen vector axis. When you call PCA in MATLAB, it returns this rotational matrix P. That's what it does. So it tells you what the rotation is. So if I do this, I get the P which is what size the P should be.
784 by 784.
Yeah. Right. And now how do I get PCA once I rotate the data? How do I say, okay, I want 3-dimension PCA?
3 columns.
Right, so I'm going to say here, give me a new data set that is, take the original X, multiply with P, but only consider, this is a syntax error. I need the columns 1, 2, 3. So this is saying in MATLAB, you got to use all the rows and just use the first 3 columns of this matrix. Right? So that's exactly what we said. We rotate it, but then we only take the first 3 columns. When you take the first 3 columns, it turns out in linear algebra you can take it before or after the multiplication is the same thing. You get the same result. So then I get this data set now, which is X3, which is the PCA version of my data set into 3 dimensions, right? I can ask for 20 dimensions, right? Again, since I have this P rotational, this is a trick, very useful. I don't have to rerun the whole PCA algorithm because I have the same rotational matrix P. I just have to cut 20 columns instead of 3 columns now.
Yeah, why are you starting with the 1 to 3?
this is columns, this already sorted in the order of eigenvalues. So the first 3 are the top 3 eigenvalues. The first 20 are the top 20 eigenvalues. All the columns will be 784 eigenvalues. Right? So now this data set, X20, is a version of, what's the size of X20 as a matrix? It should still be 70,000 data points times only now 20 columns. Right? So now I would like to see what happened. I'm going to use the labels only to evaluate PCA. So I'm not really use the labels to run PCA, but now that I have the same data set, 3 versions, 784 columns, 3 columns, 20 columns, I'm going to do the clustering. I'm going to call the k-means separately. And then to visualize those clusters, I'm gonna try to kind of dig into the data by hand and see what happened. So first of all, I'm gonna look at one label. I'm gonna say, what is this gonna do? It's gonna find me the indices of data that correspond to L equal to, L was the label, right? So that says find me all the images that were annotated as digit 2. And then I can do the same if I want to find, say, 5s, right? Find me all the indices. Those are indices that correspond to those images that were 5s. They don't have to be consecutive because the data could have come shuffled. Okay? Now I have those indices. I'm going to say, let's plot the histogram. Remember Y was the cluster IDs of k-means of the full data. And if I say histogram Y of those indices, it says I want a histogram of the cluster IDs for only the images that were annotated as 2, because this is a restriction to say only use the images that have the 2 annotation. So if I do this, MATLAB is going to plot something for me. It's going to say a histogram is like a distribution in the discrete sense. It's going to say, okay, well, the values of Y's are 1, 2, 3, 4, up to 9. That's because I asked for 10 clusters. And this corresponds to how many, this is all images that have the label 2, because I only restricted my whole thing there to images that have been annotated with 2. I was saying ask for L equal 2. Okay? So what is this saying? It's saying you have some that are assigned cluster 1, some that are assigned cluster 2, 3, 4. 8 seems to be like quite a few, and then 9 are a lot of them, and then 10 is a few. This tells me that PCA, sorry, not PCA, k-means, didn't quite organize the data in clusters corresponding to the labels, right? Clearly, most of the 2 images, the digits that are 2, went into cluster 9, and some other ones went to different clusters. But it's not too bad, right? This k-means in here pretty much took the images that are all 2s and put them in the same classes, which is what we'd expect. Most 2s look the same. They're very similar with themselves, very dissimilar with the other digits. So they will go to one cluster by a normal, cosine or dot product similarity. But there will be some 2s people write by hand. Those are digits written by people, by hand. There will be some 2s that look more like 7s or like 5 or like 3, so they went into other clusters. That's if I run k-means with all the data, the original 784 features. What would be ideal here in terms of clustering to match the labels? To be all the 2s go to one cluster and all the 5s to a different cluster and all the 7s to a different cluster. That will be a clustering that really corresponds to the digits annotation. Now, if I do the same histogram, but I want to do I have a k-means that is still into 10 clusters, but it doesn't use the original data. It uses the data that has been PCA'd into 3 features. So it does k-means, but it doesn't run the similarity on 784 features. It runs it on the 3 features that were produced by PCA. So if I histogram that, I get what? Is it better or worse? In terms of clusters, don't use the labels, right? So k-means didn't use the labels. I'm only using the labels here to kind of see if those clusters match what the human will treat as similar, digits. 2s looks like 2s, 5s looks like 5. How is this compared to the first one?
Way worse.
Much worse, right? The similarity, but remember k-means only go by similarity. If you have the same similarity, whether it's 784 dimensions or 3 dimensions, you get the same exact k-means. Because k-means doesn't look at the features, it only looks at the similarity between points. I'm counting here on the fact that you've seen k-means or you know what it is, because we clearly didn't teach that in class. So if I have the same similarity, I would get the same k-means. I don't have the same similarity, you see the plot. Because my shrinking into 3 dimensions affected the similarity function. How about the other one? I have another PCA into 20 dimensions, right? So that would be Y20 here. It's a k-means run over data that has 20 dimensions. If I plot that histogram, how does that look?
That works.
Pretty close to the original one, right? Which tells me similarity in 20 dimensions between points, that's what k-means uses, is pretty much the same as the similarity in the original space. As far as judging what point is close to what point, there must have been pretty much the same similarity with 20 dimensions. Now, maybe 20 is more than I need, right? Maybe the same thing happened with 10 dimensions. Clearly it didn't happen with 3 dimensions. 3 dimensions broke the similarity. Now, the reason this works so like a glove here is because the natural k-means similarity uses dot products. And dot products fit very well with the whole PCA notion of what I'm trying to preserve. If your similarity is based on a different functionality that doesn't go well with PCA, this argument would fall apart.
Because we're changing the axes in the coordinate system we're using, when you say limiting it to 20 dimensions, that's not saying find me the 20 pixels that have the most predicted value. It's
No.
creating a new set of coordinates.
I've already said that.
Yeah.
The axes you get in PCA are linear combinations of the original ones, except if the data is already into the coordinate system of the eigenvectors, which in that case would become a pure selection. Like from the top, choose the first one, second one, third one. But rotation means any new coordinate is actually a linear combination of the original features. That is this matrix P in there, right? The linear combination is given by the rotation matrix, and then selection is choose the first few. Well, so I'm going to look at the eigenvalues now. So I'm going to say, okay, I think I ran something here before. This is, so first of all, I want to compute S. S is the covariance matrix of X, right? I'm going to scope of X, I'm assuming MATLAB, I didn't check, but MATLAB empirical covariance estimate must be something pretty close like what we had there on the board, right? So then I look at the size of S, no surprise, it's a D by D covariance matrix. And then if I do the theory from the board, what did we do? The eigen function in MATLAB produces the C, which is the matrix of eigenvectors. That's exactly the same C we had somewhere in here. This. Right? And then D is a diagonal matrix that has the eigenvalues. That's exactly that matrix that has 0, 0, and the eigenvalues are diagonal. Right? So if I run this, I have the eigenvectors now and the eigenvalues. I would like to look at D, the eigenvalues, but that's a 700 by 700 matrix full of zeros. So I'm only looking at the diagonal of D. So there's a function that will just list the diagonal of D. And I look at it, right? And it's sorted, not the way you'd expect it, sorted backwards, but that's okay. What do we see here? How many values are here, first of all? 784. And what do we see? A lot of zeros. And how many values are not, like, significantly not zeros? Sure, significant is a relative term, right? But if I am to look at the top 20, which is what we done the PCA on last time, does it look like this top 20 will be a good approximation for the whole set of 784? Again, that's a relative question, but this is what PCA comes down to. The fact that I made those really small eigenvalues 0, they're not really 0, they're just MATLAB doesn't display enough decimals in here. Didn't cost me too much because they're already very close to 0. And you can see this in a different way. You can see this in this sum right here. In this sum, if some eigenvalues are very close to 0, that term effectively doesn't do anything, right? If this alpha d, the last one, is 0.0000 something, making that crystal 0, which is essentially taking this term out, doesn't actually change how you think of the covariance, right? So you can see that right there, that the top ones at least, that were all 0, won't do anything. Won't impact if I remove them. Now, these may be very different for different data set, right? When different data set with 784 dimensions, if I do this whole machinery here, including the k-means to try to look at it, it may be that I see 100 significant eigenvalues. And that, you have to understand that if you ask for less than what's significant, and ask for the first 3, I lose all this information, right? That's unrecoverable after PCA. One more thing I want to show you. For the white tree, right? That was the clustering into 10 clusters based on only 3 columns. Since I only have 3 columns here, I can actually plot this data, right? Because 3D I can see it. So let's see how that goes. I'm gonna plot 3 or 2 classes. So I have 3 dimensions because I asked PCA for 2 dimensions, and I have 10 classes. I could plot all 10, but that would be a busy plot, right? So I'm choosing here to plot the class of 2. That are all the images that have been labeled as 2. That we already know there's a 2 in there. And the way I'm plotting it, I'm using the x3, that's the PCA to 3 dimensions coordinates as a plot, and it's going to be red, right? Because it's asking for red. And then I've got here a plot with all the images in 3 dimensions. This is all the images that are 2s. And then if I do the same, I think I need a hold to not erase the plot. If I plot, say, I'm going to plot the 5s, that's all the images that are labeled as a 5, I'm going to plot it in blue, right? And the same 3 coordinates. I'm going to get all those images now that are 5s as blue dots in there. There's still 70,000 images, right? It's just in 3 dimensions. And I can do the same, say, for the, I don't know what that is, I copied, maybe the 7s. That's all the images that have a 7. As, say, green. So now I've got the 2s, the images that correspond to 2s, the images that correspond to 7, and the images that correspond to 5s. And I can try to look at them. That's already reduced to 3 dimensions. It's not in the original 784 dimensions. Why am I showing you this? In many problems, you gotta find yourself a tool to dig into data before you can make decisions. So what people do, they run a regression or a naive Bayes, something simple, or basic classifier. If they have to the results, nobody will bother you. You're the data scientist, right? It works, it's fine, company's doing well, no worries. You get bothered when the things don't work, right? And to make it even more interesting, the package that was run to produce that result is opaque. It's not like you can go in and make changes. It's like a binary compiled code that in principle does regression, say, or naive Bayes or something, but it's not like you can check the code and put some statements to see what happened. So what do? You gotta start digging at data. This is I found it PCA much more useful as data digger than at the dimensionality reduction, because modern algorithms don't really need dimensionality reduction that much. They can deal with dimensions. They deal with dimensionality reduction in a different way. What you need, the data scientist, is a way to know what's going on. In here, the 2s, the 5s, and the 7 are 2 intercalated to each other to make a sense of what's going on. But that's not because that's how they are in the original space. That's because 3 dimensions not good enough to do it. So one more thing I want to say before we move on to next week is how do algorithms, modern algorithms, deal with this problem of features if I don't run PCA. A particular problem for PCA is, again, I don't look at the labels. I don't do whatever I do with respect to some labels. So the PCA that I would use is supervised classification would be something that takes into account labels, not just variance over the E dimensions. What actually is happening with a lot of algorithms, especially the linear ones, they do what's called regularization. Right? We already seen this regularization. That's the L2, which we call in the first homework, we call reach. It's easy to add the reach penalty, and I think you've done that in the second homework, and even the differentiality is there in the notes because you can differentiate it. All it does, it's x plus x times x transpose becomes x transpose plus some penalty times the I matrix, which stabilizes the whole thing, aka the coefficients of regressions cannot be too high or too low. In practice, what this does, this is the constraint on the coefficients. It says, I don't want the W's, the regression coefficients, to go outside this bubble. What it does, it says, if you have correlated feature, it forces regression to spread the weight on all the correlated features. Because if I want to put, I have 3 features there, they are identical. Instead of putting a large weight on one of them and 0, 0, which mathematically would be equivalent to any linear combination of those coefficients, it forces regression to distribute that weight over all correlated features. This is much more difficult to differentiate. This constraint here, it says the norm 1 of W's cannot go outside this perimeter here, which because it's not round, has a very different behavior. Differential and the algorithm to deal with L1 regularization is much more difficult. We don't do that in class. The differential, which you can do it for the reach regression, but you can easily call a package that implements L1 for you. I recommend linear. It's a very popular package. You're not required to do that derivation. What you're going to be required is to know what L1 is. So the L1 effect is that any one of these corners is very likely to get hit much more than the sides, while this doesn't have such effect. Any part of the circle is equally likely to get hit. In here, the algorithm is a little difficult, but the meaning of this constraint is relatively easy. This is sparsity. L1 says, is the opposite of this. This one saying, spread the coefficients over correlated features. This one saying, I don't like coefficients that are non-zero. Give me only few coefficients that are significantly away from 0, make the other ones 0. Those are very complementary notions of regularization. So people that do regularization in a production system typically use both, and everyone has a penalty. So in here in this, you would see how this actually looks like. This is the new objective for regression. This is the regression loss. This is called a penalty term. And now this penalty, if it's simply L2, is just the L2 norm, the whole R. The penalty depends on the parameter zone, that is the W's. And if it's L1, it's it will be the norm 1 of the coefficients that corresponds to that rhombus there. And if I want to use both, I will need to have a penalty that's some combination of L2 norm and some combination of L1 norm. And now this would be called elastic net. That's what people use in production when they run regression usually. Elastic net, which is regression with a ridge and lasso. And lasso is L1 penalties. However, the difficulty with this is that it's kind of hard to estimate what parameters I need on these penalties. So the only way to do that, to not rely on assumptions, is to try different parameters and retrain your regressor with different regularization parameters on and on and on, which could be a problem if I don't know how to search for parameters. And in typical problems, we don't know how to search for parameters. So you'll see a lot of production system that could be quite easy to train, but is being trained 1,000 times with different regularization parameters. That's called tuning for hyperparameters. And then instead of a simple algorithm computationally, I get a very complex algorithm computationally because I have to retrain that thing so many times. We have this problem in production right now. I told you guys in consulting, regression will do the right job with the right parameters, but to find those parameters, we have to tune those models. Most of the money being spent on Amazon servers is this regression hyper-tuning parameters. So that's part of your homework. I expect you guys to know the L2 derivation, which is very similar to the original regression derivation, but not the L1 derivation. So for L1, you're going to have to use a package like liblinear to run it. As an extra credit, of course, you can implement your own elastic net. That means following some L1 derivation and write regression that way. There is something we didn't do. I'm going to stop right here. There's something we didn't do for your homework, so we'll have to do it on Tuesday. That is images, higher features, right? So we didn't do that. That's something very simple. I'll do it Tuesday in class. It has to do with how to cut chunks of an image as a feature, right? So you take an image, it's 3000 by 2000 or 28 by 28. How do I cut pieces of it and make features out of that? You can easily follow those. It's a high school level in terms of intellect. The only thing I have to say there is something about how to do it efficiently, and I'll do that on Tuesday. And if that means we need more time for the homework, so be it. I might come.
I have a question about